Hi guys, in this video we discuss arithmetic of Euclidean domain. First we have a theorem. For Euclidean domain D with a Euclidean norm V, the first statement is norm of 1 is the minimal of all norm of A not equals to 0 belongs to D. Here is the proof. Norm of 1 is less or equals to norm of product of 1 and A, and that equals to norm of A. This gives us norm of 1 is less or equals to norm of A for all not equals to 0 belongs to D, and this clearly shows norm of 1 is the minimal of all norm of A not equals to 0 belongs to D. Proved. Now the second statement of the theorem. It states U belongs to D is a unit if and only if norm of U equals to norm of 1. We have the proof here. For the first part of the proof, U belongs to D is a unit is given to us, and this implies there exists U prime belongs to D such that product of U and U prime equals to 1 from definition of unit. Now we have norm of U is less or equals to norm of product of U and U prime from the second condition of Euclidean norm, that equals to norm of 1 from this relation. So we have norm of U is less or equals to norm of 1, but norm of U less than norm of 1 is not possible. Why? Because from our earlier statement, norm of 1 is the minimal of all norm of A for A belongs to D. So this gives us norm of U must be equals to norm of 1. Now the second part of the proof, norm of U equals to norm of 1 is given to us, and since D is a Euclidean domain, we have Q and R belongs to D such that 1 equals to U times Q plus R, where either R equals to 0 or norm of R is less than norm of U. But we have norm of R less than norm of U is not possible because norm of U equals to norm of 1, which is the minimal norm of all U belongs to D. So we must have R equals to 0, and this gives us 1 equals to U times Q. This shows U is a unit from definition of unit. Hence, U is D is a unit if and only if norm of U equals to norm of 1. This proves the theorem. The next topic we have is Euclidean algorithm for computing G-series. Now every Euclidean domain, it is equipped with Euclidean algorithm for computing G-series. So if an integral domain is an Euclidean domain, we can always use Euclidean algorithm for computing G-series in that integral domain. Now factoring to compute G-series in an integral domain is not always an option because factoring can get very tough in some integral domain. In that case, the Euclidean algorithm is a necessary tool for computing G-series. Now the statement of Euclidean algorithm, let D be an Euclidean domain with Euclidean norm V, then for AB belongs to D, there exists Q1 R1 belongs to D such that A equals to B times Q1 plus R1, and we have B equals to R1 Q2 plus R2, and likewise Ri minus 1 equals to Ri Qi plus Ri plus 1, and the sequence of R1 R2 dot dot must terminate with some Rs equals to 0. Now if R1 equals to 0, B is the GCD of A and B. But if R1 not equals to 0, then for some I, Ri equals to 0, in that case Ri minus 1 is the GCD of A and B. Now let us illustrate the Euclidean algorithm by computing the GCD of 12 and 32 in integers. We have 32 equals to 12 into 2 plus 8. R1 not equals to 0. So 12 equals to 8 into 1 plus 4. Again, remainder not equals to 0. So 8 equals to 4 into 2 plus 0. Finally, remainder equals to 0. So by Euclidean algorithm, this 4 is the GCD of 12 and 32. And this ends our lesson.